Voyager 2 launched in 1977, running on computers weaker than a calculator. It was only built to fly past planets, not to survive this long. In 2018, it reached a place no working instrument had ever touched before. A boundary scientists had only ever guessed about. What it measured there did not match a single prediction. The spacecraft that refused to quit. Voyager 2 launched from Cape Canaveral in August 1977, technically before its twin Voyager 1, even though Voyager 1 ended up further ahead in space. The plan was simple on paper. Use a rare lineup of the outer planets to fling one spacecraft past Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity as a slingshot. Nobody had ever flown past Uranus or Neptune before, and nobody has since. Voyager 2 remains the only spacecraft in history to visit both of those planets up close. That kind of planetary lineup only happens once every 176 years. And engineers in the 1960s realized it would let a single spacecraft use each planet like a stepping stone, gaining speed from one flyby and aiming itself straight at the next. Miss that launch window, and the same free ride would not come around again until the next century. Voyager 2 took it, and by the time it passed Neptune in 1989, it had spent 12 years crossing the solar system and sent home the only close-up pictures humanity has ever had of that planet's clouds and rings. The mission was originally planned to last 5 years. It has now been running for close to 50. Along the way, it carried something strange bolted to its side, a golden record loaded with sounds and images of Earth, along with instructions and symbols for how to play it, meant for anyone or anything that might one day find it drifting between the stars. By the time it finished its planetary flybys, most people assumed the exciting part of the mission was over. What nobody expected was that the most important discoveries were still decades away, waiting at a boundary nobody had ever physically touched before. Can see. The sun does not just light up the solar system. It also blows out a constant stream of charged particles called the solar wind, fast enough and dense enough to carve out a massive bubble around the entire solar system. Scientists call that bubble the heliosphere. Everything inside it, every planet, every moon, every spacecraft we have ever launched until recently has spent its entire existence surrounded by particles that came from our own star. Outside that bubble is something completely different. A thin, cold soup of particles left behind by other stars that exploded and died millions of years ago. Scientists call it the interstellar medium. The edge where the solar wind finally gives up and the interstellar material takes over is called the heliopause. And for most of human history, it was a line on a diagram, not a place anyone had measured directly. Between the two lies a rougher region called the helios sheath, where the solar wind has already slowed down but has not yet been stopped completely. Voyager 2 spent years crawling through that in-between zone before it ever reached the true edge, giving scientists a long, slow preview of conditions getting stranger the further out it traveled. Voyager 1 became the first machine to cross that line in 2012. Nobody knew exactly what would happen the moment a spacecraft actually reached it. 6 years later, Voyager 2 got the chance to check the answer a second time, and this time, it had a working instrument that Voyager 1 no longer had. The day the solar wind disappeared. On November 5th, 2018, something on Voyager 2 changed all at once. Its plasma science instrument, which measures the speed, temperature, and density of the charged particles flowing around the spacecraft, recorded a sharp drop in the speed of the solar wind. Then the readings dropped to nearly nothing. At the same time, instruments built to count energetic particles from the sun saw those particle counts fall off a cliff, while counts of cosmic rays coming from outside the solar system spiked upward. Every instrument was telling the same story from a different angle. The solar wind that had surrounded Voyager 2 for its entire 11 billion mile journey had simply stopped. It had become the second spacecraft in history to leave the heliosphere at a distance of about 11 billion miles from Earth, well past the orbit of Pluto. Ed Stone, the mission's project scientist for nearly 50 years, said at the time that there was still a great deal left to learn about the region immediately beyond that boundary, even with a second spacecraft confirming what the first one had found. His caution turned out to be well placed, because the numbers Voyager 2 sent back over the following months did not simply repeat what Voyager 1 had already shown. What made this crossing special was that the plasma instrument on Voyager 1 had stopped working back in 1980, decades before that spacecraft reached the same boundary. Voyager 2's version was still running perfectly. For the first time, scientists had a working plasma detector actually sitting at the edge of the solar system. And what it found next is where things got strange. Something that broke the models. A year after the crossing, NASA released 5 separate research papers in the journal Nature Astronomy, each one built around a different instrument on Voyager 2. Taken together, they painted a picture nobody had drawn before, and parts of it did not match what physicists expected going in. Scientists confirmed that the plasma sitting just outside the heliosphere was noticeably denser than the plasma inside it, exactly as predicted in theory. But Voyager 2 also measured that plasma as slightly warmer than models had forecast, even though it was still colder overall than the plasma inside the bubble. Right at the inner edge of the boundary, just before the crossing, the plasma also showed a small spike in density, suggesting it was being squeezed and compressed right where the solar wind pushes back against the outside universe. The magnetic field data told its own part of the story. Instead of a tidy, symmetrical bubble, the magnetometer results suggested the entire heliosphere is being pressed and reshaped by the pressure of the interstellar medium pushing back against it. The same kind of squashing effect scientists had suspected but never confirmed with a second spacecraft's instruments. Researchers at the University of Iowa, who led the plasma wave side of the analysis, described the crossing as producing a clear, unmistakable jump in density the moment Voyager 2 passed through, a signature that confirmed the spacecraft had truly left the world shaped by our own sun and entered the space between stars. It was the kind of direct, physical confirmation that theory alone could never fully provide. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. None of that matched a perfectly smooth, predictable line separating two regions. The boundary behaved more like a rough, active shoreline than a clean wall, and that discovery would not have been possible without an accident of engineering nobody planned for. One instrument on Voyager 1 breaking decades earlier, while its twin kept working all the way to the edge. The warning nobody believed at first. This was not even the first time a Voyager spacecraft had stumbled into something unexpected near the edge of the solar system. Back in 2007, as Voyager 2 crossed an earlier boundary called the termination shock, where the solar wind first starts slowing down, MIT researchers running the plasma instrument found 2 surprises at once. The first was a magnetic field in that outer region far stronger than anyone had calculated, strong enough to be squashing and distorting the shape of the entire solar bubble, instead of leaving it a smooth, even sphere the way earlier models assumed. The second was even stranger. Just outside that shock boundary, the plasma temperature came in about 10 times cooler than predicted, even though it was still hotter than the plasma deeper inside. Theorists scrambled afterward to explain the missing heat, eventually deciding that energy was likely going into particles moving too fast and too hot for the plasma instrument itself to measure. The lead scientist on that instrument, John Richardson of MIT, called it a different kind of shockwave than anyone had seen before anywhere in space. He presented those findings at a meeting of the American Geophysical Union in San Francisco, where they caught the attention of space physicists who had spent decades building models of a much calmer, more predictable boundary. That earlier surprise turned out to be a preview of a much bigger pattern. Every time Voyager 2 reached a new boundary, the numbers refused to line up neatly with the models built from Earth. 11 years later, the spacecraft was about to prove that pattern one more time, right before it nearly went silent for good. The 2 weeks nobody could talk to it. In July 2023, a routine set of commands sent to Voyager 2 accidentally tilted its antenna about 2 degrees away from Earth. 2 degrees sounds tiny, but at a distance of more than 12 billion miles, it was more than enough to break the link completely. The spacecraft could no longer receive commands, and it could no longer send data home. For almost 2 weeks, mission control had nothing but silence. The backup plan was built into the spacecraft itself, a fault protection system programmed to automatically reset its orientation and point back toward Earth. But that safety reset was not scheduled to trigger until mid-October, months away. Engineers were not willing to simply wait that long and hope nothing else went wrong in the meantime. NASA relies on a network of 3 giant dish antennas spread across the globe, in California, Spain, and Australia, so that as Earth rotates, one dish is always facing whichever direction a distant spacecraft happens to be. It was the dish in Canberra, Australia, that first picked up a faint carrier signal from Voyager 2, too weak to carry any actual data, but strong enough to prove the spacecraft was still alive out there. On August 2nd, 2023, that same Canberra antenna sent what engineers nicknamed an interstellar shout. A high-powered signal blasted across more than 12 billion miles, instructing the spacecraft to turn its antenna back toward home. The command took over 18 hours just to arrive, and another 18 hours for any response to come back. A full day and a half of waiting with no idea if it had worked. Just after midnight on August 4th, Voyager 2 answered. It began sending science data again like nothing had happened. The spacecraft had survived, but the scare made it clear how fragile a 50-year-old machine really is once something goes wrong that far from home. Surviving that scare bought Voyager 2 more time to keep exploring, but time was never really the problem chasing this mission. The real threat was something slower and far harder to fix. A battery that has been quietly running down since the day it launched. The slow countdown, nobody can stop Voyager 2, does not run on solar panels. It runs on heat given off by decaying plutonium, a power source that naturally weakens over time no matter what engineers do. Both Voyager spacecraft lose about 4 watts of power every single year, a number that never goes up and never pauses. There is no way to refuel it, no way to send new batteries, no repair crew that could ever reach it. To stretch the mission as long as possible, engineers have been shutting down instruments one at a time since the 1980s, starting with tools that were only useful for studying the giant planets. Out of 10 original science instruments, 6 had already been switched off before 2024 ever arrived. Along with heaters and other onboard systems, engineers decided the spacecraft could survive without. Every remaining watt now goes toward keeping the surviving instruments and the radio system alive. By 2024, the choices left were far more painful. In September of that year, the team switched off the plasma science instrument itself, the same instrument that had confirmed the spacecraft left the solar system back in 2018. Engineers said the instrument had already been giving limited readings for years anyway. Because of the direction Voyager 2 happened to be facing, relative to the flow of interstellar plasma. By March 2025, the low-energy charged particle instrument was shut down too, leaving only 3 tools still running: a magnetometer, a cosmic ray detector, and a plasma wave instrument. Engineers expect the cosmic ray instrument to go dark sometime in 2026. After that, only 2 instruments will remain, and even those cannot last forever on a power source that keeps shrinking every year without exception. What happens when the signal finally stops? NASA believes Voyager 2 can keep running with at least 1 working science instrument into the 2030s, more than 50 years after its launch. Even after every instrument eventually goes silent, the spacecraft itself will keep moving, carrying its golden record further into the dark long after anyone on Earth can hear from it again. Voyager 1 is further along that same road already, having lost its own plasma instrument decades ago. Watching both spacecraft fade out step by step gives scientists a slow, careful shutdown of the only working eyes and ears humanity has ever had this far from home. What it already sent back cannot be replaced. It proved that the boundary of our solar system is not a clean, empty line, but an active, uneven shoreline of compressed plasma and shifting magnetic fields. It survived a communication blackout that could have ended the mission instantly. Somewhere past Pluto, moving further from home every second, Voyager 2 is still out there right now, carrying instruments built in the 1970s into a region of space that did not behave the way anyone on Earth expected it to. Until its last signal ever arrives, it keeps going. The only working eyewitness humanity has ever had at the true edge of the solar system. If you enjoyed this video, make sure to subscribe, and I'll see you in the next one.